Back. This is Mr. Hassan's Maths channel. I'm now answering question number 8 from the October 2024 Pure Mathematics P3 exam from Edexcel International A-Level. And here we're told about this graph which shows a heart rate of a horse that is being monitored. The heart rate H, which is measured in beats per minute, is modeled by the equation H equals 32 plus 40 times e to the power of negative 0.2t minus 20 e to the power of negative 0.9t, where t minutes is the time after monitoring began. So it says figure 4 is a sketch of H against t. It says use the equation of the model to answer parts A to E. So it says state the initial heart rate of the horse. So the initial heart rate of the horse would be that value when time is 0. Okay, so that's simply what that means. So the initial heart rate of the horse can be found by just replacing t with 0 in our equation. So we know that when t is equal to 0, h is going to be 32 plus 40 times e to the power of 0, basically, because you're going to put minus 0.2 times 0, minus 20 times e to the power of, again, 0. And we know that e to the power of 0 is equal to 1. Anything to the power of 0 is equal to 1. So e is just a number. Okay, it's called the natural number. So this is going to give you 32 plus 40 minus 20. So that's going to be basically 32 plus 20, which is 52. So it says state the initial heart rate of the horse. So we should state it as 52 beats per minute. Okay, put the unit there. Asking for the heart rate, so we should put the unit down. Okay, it's very important for us to understand that. They ask you in this way, like for example here in part B, it says in the long term the heart rate of the horse approaches L BPM. State the value of L. So in this case, the units of L are defined in the question. So here you just have to write down the value of L. You don't write down the unit with it. You don't have to write down the unit with it. Technically, you should just write down the value. In this case, you know, it's saying find the initial heart rate of the horse, so you should put beats per minute. Okay, that's the difference between these two kind of wordings of the question. So in the long term, the heart rate of the horse approaches L beats per minute. State the value of L. So what we should do is, let's think about this as time approaches infinity. The long term means as time gets closer and closer to infinity, gets much larger and larger. Long term, when time is very long, you could say. That was mathematically what that means in the long term. That's how you can think about it. So if we have h equals, and now I'm going to rewrite this as 40 over e to the power of 0.2t minus 20 over e to the power of 0.90. I've just rewritten this in the form because I know, for example, that a to the power of negative n is 1 over a to the power of n from the laws of indices. So I've just done the same thing. This is like 40 times 1 over e to the power of 0.2t. This is like 20 times 1 over e to the power of 0.90. Okay, so that's how we can rewrite that. So as t gets larger, as t approaches a very large number, then e to the power of 0.2t, okay, will basically become e to the power of a very large number, right? So you're going to have, this will become, so you can say 40 over e to the power of a very large number is going to approach 0. If you divide something by a really huge number, e to the power of a very large number will approach a really large number as well. So this will be 40 over a really huge number, which will approach 0. So as t gets really, really big, this is going to become really, really small. Okay, and so is this. So you'll have h is going to be approaching. So as t approaches a really large number, then h will approach 32 plus 0 minus 0, because 20 over e to the power of 0.9t is going to approach 20 over some really huge number, which approaches 0. Just as 40 over e to the power 0.2t will also do the same thing. So these two, as the value of t gets really huge, the denominator gets really big, so this fraction becomes really small. When you divide something by a really big number, it becomes really small. The bigger that number in the denominator becomes, the closer and closer the value of that fraction gets to 0. Okay, so we can see that the value of L is the value that is 32 basically. It's going to be 32 because both of these will approach 0. Now, it just says state the value L. You don't have to show any of these steps. Okay, this is just to get you to understand the reasoning why it becomes that. What you could do if you want to, no problem, in the calculator, you can just take this expression, 32. In fact, you can take the original equation without even rewriting it. So 32 plus 40 times e to the power of, which is given by this button over here, e to the power of negative 0.2. And I'm going to put in here a number, so times, like for example, 1,000. A big number. Don't put it too big, otherwise it might give you a math error. It might not be able to deal with it. Minus 20 times e to the power of minus 0.9, so negative 0.9 times, again I'll put t as 1,000 just to make it a big number. Right. If the number 1,000 is too big, it might say math error. You could make it smaller, but let's see what happens. See here we can see it's approaching 32. The answer becomes 32 because this gets so close to 0 and so does that they're just like negligible. So doing this will help you to find the answer, okay? And you don't really have to show these steps here at all. It's just one mark. It says state the value of L. So you could just look at this and understand what we just mentioned here. Or if you want to, you could just put the value of t. This is a long term, t is a big number. T is big, time is a big time. You can put a big number instead of t and see what the calculator gives you. Now, if it gives you a math error, for example, I don't know if this is going to actually happen, but supposing I put, for example, an extra 5 zeros, 1, 2, 3, 4, 5. And I do the same for here. It might still give me the answer, but sometimes you can't handle it. So 1, 2, 3, 4, 5. It still works, that's fine. Okay. Sometimes it doesn't. In certain types of questions, it might not be able to handle such big numbers, and it might give you an answer that says math error. Just choose a smaller number. In this case, it seems like it's fine. So there's the answer to part B. Okay, now for part C, it says the heart rate of the horse reaches its maximum value after t minutes. Find the value of t, giving your answer to 3 decimal places. Okay, so the maximum value, as we can see from the graph, the maximum value is going to be the point at which the curve turns. Okay, so it's going to be this point over here, right, where the curve turns. That's going to be the maximum value. Okay, that will be the point at which the heartbeat reaches maximum value, and we want to find the time at which that occurs. So what we're trying to find here is the value of this time when that maximum occurs. So the maximum occurs at this point, the highest point, where basically the gradient of this curve, which is the change in h over the change in t, which you can express as dh dt, instantaneously becomes 0. So the first step is for us to find dh dt. So the maximum value of h, okay, is when dh dt is equal to 0. The first step is to find dh dt. So when you differentiate something like this, the constant becomes 0. Now, if I differentiate e to the power of x, for example, with respect to x, one of the features of the b natural number, e to the power of something, is that it doesn't change. So this stays as e to the power of x. However, if you have a function within the function, like e to the power of some constant times x, some function times x, and you differentiate that with respect to x, then you have to differentiate what's inside the function, which gives you k, and multiply it by the function as it is, because it doesn't change when you differentiate it. But you have to use the chain rule. So in this case, we're going to do the same thing. So we got to have plus. Now, this is the function inside the function. This thing won't change. It will stay as 40 times e to the power of negative 0.2t. But we have to multiply by negative 0.2, the differential of what's inside the function. And that's times 40 e to the power of negative 0.2t. And similarly to this case, you've got minus, and you're going to have the differential of what's inside the function, which is negative 0.9 times 20 e to the power of negative 0.9t. Kind of going out of space there. Now we can simplify this. So dh dt is going to be, that's 0.2 times 40. That's going to give you 8. That's going to be 8. That's right. So that's 8 times e to the power of negative 0.2t. And minus times minus is plus. And this is negative, by the way. This is negative, by the way, because you have, that's a minus there. And this is minus times minus, which is plus. Now 9 times 2 is 18. So that's going to be 0.9 times, yeah, that's going to be 18. So it's plus 18 e to the power of negative 0.2t. Right, so that's the gradient function for our expression here, or equation here. Now we want to find when dh dt is equal to 0. So to make dh dt equal 0, I'm going to write this first just to make it a bit simpler. So 18 times e to the power of negative 0.9t minus 8 times e to the power of negative 0.2t equals 0. Now, I think that one of the ways to deal with this is by using, factorizing. We always try to avoid dividing by a variable if we can. So what I'm going to do is I'm going to, first of all, divide by 2. So this is 9 e to the power of negative 0.9t minus 2 e to the power of negative 0.2t equals 0. And when you factorize something which is raised to a power, we normally take out the one with the lowest power. The one with the lowest power. We take that out. And what's smaller, minus 0.9 or minus 0.2 was minus 0.9. So I'm going to take e to the power of, I'll just make some space here. So I'm going to take out e to the power of negative 0.9t as, say, a common factor. There's other ways we can do this. I'll show you as well how to do that later as well. So here I'm going to have 9. Okay. Minus, and then I need a 2. And then I need to end up with e to the power of negative 0.2t when I multiply these together. So I have to have e to the power of something. Now I know that e to the power of negative 0.9t times e to the power of, let's call it x, there's no x's here, is equal to e to the power of negative 0.2t. So I know these powers must be added together to give me that. When I multiply two numbers in index form, I add the powers. So basically I can say 0.9 minus 0.9t plus this x is equal to negative 0.2t. So x is going to be negative 0.2t plus 0.9t, which is going to be 0.7t. So here I have to have 0.7t. Okay, so when I multiply this by this, I end up with 2 to the power 2 times e to the power of negative 0.2t, which is what I want there. So I've now factorized this expression. So I have either this part equals 0, which actually can never happen, because if you think about it, e to the power of something looks like this. When I put it as minus 0.9 to the power of t, it's going to be something like this. Okay, and it never ever reaches this, it never becomes 0. Okay, so there's no solution to this part. And this part here, I can say 9 minus 2 e to the power of 0.7t equals 0. So I can solve this. I can say 9 is equal to 2 times e to the power of 0.7t. So I can write this as 9 over 2 equals, made a mistake again, sorry. let me go back here. 8 divided by 2 is 4. Just notice that here. So let me just correct that. So those of you who've already commented on the video, so you made a mistake. I found it before I finished, so I won't edit this out. I'll just leave it as it is. Can't be bothered. Okay, so you have, this is going to be 9 over 4. Remember, because I divided it here, I divided by 2. For some reason I put 2 here and it's 4. 80 divided by 2 is 9. Okay, good. So that gives me e to the power of 0.7t is equal to 9 over 4. I want to find what t is, which is trapped in the power. So I want to take the log to the base of the number to which it's been raised. So I can see that that number is e. So if I take log to the base e, that's ln. So I'm going to take ln of both sides. So ln of 9 over 4 equals basically 0.7t. So we can say that 7 over 10t equals ln of 9 over 4. So that means t is equal to 10 over 7 times the ln of 9 over 4. And that will give us our answer. And that is basically our capital T is equal to this t here that we found is equal to capital T, because it's when dh dt is equal to 0, and that's what we just found. So we can now say that the capital T that we're looking for, is going to be this, and we want it to how many? 3 decimal places. So we want this to 3 decimal places. So we'll take a calculator. So we have 10 over 7 times the ln of 9 over 4. And that gives us 1.15847. So 1.5, what was it? 1.15847, 3 decimal places. That's going to be 1.158. And that was in what units? Minutes. Okay, in fact, we don't have to put minutes. We can leave it like this because t is defined in the question as being in minutes. So we don't have to put minutes here. We just put 1.158 to 3 decimal places. And there's the answer to part C of this question. Okay, and now we want to find part D. So it says the heart rate of the horse is 37 beats per minute after m minutes. Show that m is a solution of this equation. Okay, so we know that 32 plus 40 times e to the power of negative 0.2t minus 20 times e to the power of negative 0.9t is equal to 37 when t equals capital M. Okay, so I'll find the values of t and then I'll decide which one of them, if there's more than one, which relates to M. Okay, so now I need to solve this. So I can subtract 32 from both sides first. So I have 40 e to the power of negative 0.2t minus 20 e to the power of negative 0.9t is equal to 5. 7 minus 32. I can see 5 is a common factor of all of these terms. So I can divide everything by 5. I have 8 e to the power of negative 0.2t minus 4 e to the power of negative 0.9t is equal to 1. Now, how can I deal with this? I have to find the value of t. I have to show that t is a solution to this equation here. Okay, so basically what I have to do here is I don't have to solve this. I have to just show that t equals this. So basically one of these t's has been made the subject of the formula. And because I've got minus 0.9t here, right, it must be this t that's been made the subject of the formula. This looks like it's going to become an iteration question because that's t in terms of t. So it's this t that must be made the subject of the formula. Why? Because we have minus 0.9t. Okay, so I need to make this the subject of the formula. So I'm going to start off by making this term the subject and then deal with the e. So first of all, I'm going to add this to both sides. So I have 8 times e to the power of negative 0.2t is equal to 1 plus 4e to the power of 0.9t. Starting to look familiar now. And then I'm going to have, let me make some more spaces, some more space here. Okay, so now I'm going to have divide by 8, so e to the power of negative 0.2t is equal to 1 plus 4 e to the power of negative 0.9t. Should be negative, right? That's right. I forgot to write the negative there. Divided by 8, just divide both sides by 8. Now, this can be rewritten as e to the power of 0.2t. That's like the reciprocal of this. If I have a to the power of minus n, okay, it's like 1 over a to the power of n, right? So if I write this as its reciprocal, okay, it's going to be e to the power of 0.2t. It's like I've turned it upside down. So it's like I started off with this, 1 over e to the power, I've rewritten this as, okay, this, the reciprocal of this is going to be e to the power of 0.2t. So if I write this side as its reciprocal, then I must write this side as its reciprocal as well. So I have 8 over 1 plus 4 e to the power of negative 0.9t. And now I need to take the ln of both sides. Okay, so if I take the ln of both sides, I'm running out of space. I think I'll go over to the next page eventually. Let me just move this down further. If I take the ln of both sides, this becomes 0.2t, and this becomes the ln of 8 over 1 plus 4 times e to the power of negative 0.2t. And if I divide by 0.2, now remember 0.2 is the same as 1 over 5. Okay, 0.2 is 1/5, right? That's 2 over 10, so 1/5. So t is going to be 5 times the ln, because I multiplied by 5 to get rid of this, So 5 times the ln of 8 over 1 minus 4 times e to the power of negative 0.2t. And that's what we had to show. So that is going to be m. Okay, so in this case, t is equal to m. So you write m equals, and you write m equals. Okay, so there we have the answer to question. So this is 0.9 here. What am I doing? Sorry about those few little mistakes you've got to be careful of. That's copying error. Okay, so how did I know to make this the subject? Because I can see that what we're left with is this term here, e to the power of negative 0.9t. So that was left alone, and this was made the subject. Okay, that's how I knew which one to make the subject. So there's the answer to question number 8, part D. It's a long question. Now part E is using iteration. So it says use the iteration formula to find the value of T2 and then to find the value of M. T1 equals 10. So M is basically the value of T when this happens. So I have to just basically use the iteration formula just to show what T2 is, and then keep on doing the same iteration, and that will give me the value of M. We'll get closer and closer to it as I keep going. So this basically helps us to home in on the actual solution, okay, getting more and more accurate each time as we go along. So we start off with the initial value of T as 10. So if I want to find T2, so this is part 1, if I want to find T2, I just use this iteration formula. So 5 times the ln of 8 over 1 plus 4 times e to the power of minus 0.9 times T1, which is 10. Okay, that's going to give me T2. Right, now what I'm going to do, I'm going to set up in a particular way that will help me to answer the question very easily for especially part 2. So what I'm going to do is I want T1 to be 10. So that's going to be the value that we start with. I'll press 10 and then equals. This is now saved in my calculator, okay, as the answer. This is the answer in my calculator now, right? Press answer equals is going to be 10, right? So now what I'm going to do is I'm going to set this up. So I have 5 times ln. I'll have 8 over 1 plus 4 times e to the power of negative 0.9 times, I'm going to put answer here. I'm not going to put 10, I'm going to put answer. At the moment, answer is 10. Okay, now what's this? This will help us, as you'll see in a minute. So I'm going to press equals, I'll get the answer for T2. That gives me 10.39474. 10.39474. It goes on, so to 4 decimal places, 10.3947. There's the answer to part 1. Now for part 2, we got to find what T3 is. So all I need to do now is just continue just putting that value in. So if I press equals again now, that will give me the next value, 10.39547. 10.39547. And it continues a couple more. 7477. Okay. And T4, I'm not going to round it until after I've got to the answer at the end. So this will settle down hopefully to something which is going to get to quickly. So you got 10.39547. Okay, so it looks like it's settled down already. 5478. Okay, that continues like this. And I'll do another time, and hopefully, so you've got the first 4 decimal places. At the moment, they seem to be settling down to a particular value. Press equals again. It's settled down now, basically. The 4th, we can just stop there. Okay, so that's going to become, so we can say M is equal to 10.3955. Okay, that's the value of M. M is stated already. It's in minutes. We don't have to put minutes. And there we have the answer to part E, part 2. That concludes this question, which is all about, well, different things actually. Starts off with exponential model, okay, and it's a bit of differentiation, okay, and then we had iteration basically. So there's a few different topics here which I've kept in one whole video, but no problem. So that concludes this question. Thank you for watching. I hope that was clear. And other questions from this paper can be found in the playlist up here, linked over there. Other questions from the topic of exponential models can be found in the playlist down here. And differentiation, you can find the link over here. And for numerical methods and iteration up there. Thank you for watching, and see you.